acceleration from ground to some height. Human used to light the fire. The chemical reaction 746 watts. Introduction. Papa, I like this place so much. This park is so beautiful and it is full of nature. Yes, son. That is the reason why we come here daily for the morning walk. Papa, why is that cyclist looking so tired? He is looking so tired because he is losing his energy. Energy? Yeah, my science teacher taught us about energy last week. Great, son. But do you also know about the work and power? No, Papa. Okay, let me explain you. That boy riding the bicycle is called work done. The capacity of that boy for how much time he will ride this bicycle is called energy. And rate of doing work at that what speed he rides the bicycle is called power. Now, let's take a brief look on work, energy and power. Objectives. At the end of this lesson, you will be able to define work, energy and power, measure work done, calculate work done by a variable force, define kinetic energy and potential energy, learn work energy theorem, learn work energy theorem for a variable force, learn various forms of energy, understand about conservation of energy, understand collisions. Definition. In our daily life, we can see many examples of work, energy and power. A swimmer swimming in a swimming pool, a boy running in a game, a man lifting and carrying a heavy box from one place to another place. In all scenarios, work, energy and power are used. Work. The work done by the force is defined to be the product of component of the force in the direction of the displacement and magnitude of this displacement. W is equal to F into D. W is equal to F cos theta into D. Work done is zero in the following conditions. When the force and displacement are mutually perpendicular. When the force is zero. When the displacement is zero. Kinetic energy. Kinetic energy is the energy possessed by a body by virtue of its motion. Kinetic energy is equal to half mv square. Running water, flying bird are few examples of bodies possessing kinetic energy. It is logical that a body moving with a higher speed should possess more kinetic energy than a body moving with lower speed. Example. Let's take an example of kinetic energy. A body of mass 10 kg initially at rest is subjected to a force of 40 Newton. Calculate the kinetic energy acquired by the body at the end of 20 seconds. Let's see the solution. Given values are m is equal to 10 kg, u is equal to 0, f is equal to 40 Newton, t is equal to 20 seconds. By using v is equal to u plus 80, we get v is equal to 80 meter per second. Kinetic energy is equal to half mv square. On calculating, we get kinetic energy is equal to 32,000 joules. Work done by a variable force. When the displacement delta x is very small, then work done is given by delta w is equal to fx delta x. Now, adding successive rectangular areas, total work done is given by w is approximately equals to summation from initial position xi to final position xf of product of fx and delta x. By adding the areas of all the rectangles, we find that for delta x tends to 0, the area under the curve is exactly equal to the work done by fx. Work energy theorem. The change in kinetic energy of a particle is equal to the work done on it by the net force. Kf minus Ki is equal to W. Here, Kf and Ki are final and initial kinetic energies of the object respectively. Work refers to the force and the displacement over which it acts. Work is done by a force on the body over a certain displacement. Work energy theorem for a variable force. Here, force is continuously varying in one dimension. By calculating dk by dt equal to d by dt into half mv square, we get dk upon dt is equal to f into dx by dt, which gives dk is equal to f dx. Now, integrating from the initial position xt to final position xf, we have kf minus kt equals to work. Hence, the work energy theorem is proved for a variable force. Work energy theorem involves an integral over an interval of time. It should be noted that it is in scalar form. Potential energy. Potential energy is defined as the energy possessed by a body by virtue of its position or shape. For example, water stored in a dam, stone placed on a hill, a stretched bowstring, etc. When a body is lifted without acceleration from ground to some height, work is done against gravity, and this work done gets stored in the body in the form of potential energy. Potential energy is equal to change in work done. So, potential energy is equal to mgh. Now, body is dropped down and it comes with an increasing speed. Just before it hits the ground, its speed is given by v square is equal to 2gh. This equation can be written as half mv square equals to mgh. Conservation of mechanical energy. The principle of conservation of total mechanical energy states that the total mechanical energy of a system is conserved if the forces doing work on it are conservative. Let us understand it with an example. Consider a body of mass m initially placed at point B at height h from the ground. The mechanical energy of the body at B is mechanical energy of the body at B is equal to kinetic energy of the body at B plus potential energy of a body at B is equal to 0 plus mgh is equal to mgh. Let A be a point at a distance x from B, and if u be the velocity of the body at A, then u square is equal to 2gx. Mechanical energy of the body at A is equal to kinetic energy of the body at A plus potential energy of a body at A. By calculating it, we get the mechanical energy of the body at A is mgh. If v be the velocity of the body just before hitting the ground, then v square is equal to 2gh. Here, mechanical energy of the body at O is equal to kinetic energy of the body at O plus potential energy of the body at O. By calculating it, we get mechanical energy of a body at O is mgh. It is clear from all above equations that mechanical energy of a body remains conserved during its free fall. Potential energy of a spring. When a spring is stretched or compressed without acceleration, some work is done by an external force. This work gets stored in the spring in the form of potential energy. When the spring is stretched or compressed, a restoring force is set up in the spring due to its elasticity, which is directly proportional to the change in its length. Restoring force is given by F is directly proportional to x. F is equal to minus kx, where k is equal to force constant of the spring and negative sign shows that it always acts in the direction opposite to the change. Then, external force required at this instant is given by F is equal to kx. Work done by the external force in further changing its length by dx is dw is equal to dot product of F vector and dx vector or dW is equal to kx dx. Now, the total amount of work done by the external force in changing its length by L is given by W is equal to integration of dW. By calculating it, we get W is equal to 1 upon 2kl square. Then, potential energy of a spring on changing its length by L is potential energy is equal to W. Potential energy is equal to half kl square. Various forms of energy. Energy comes in many forms, which transforms into one another. These are heat energy, chemical energy, electrical energy, nuclear energy. Heat energy. Let us take an example for better understanding. In ancient time, humans used to light the fire with the help of rubbing stones. Here, work done by the friction is transferred as heat energy. This raises the internal energy of the stones. When the temperature of stones rises enough, then a fire spark produces. Chemical energy. It arises from the fact that the molecules participating in the chemical reaction have different binding energies. A chemical reaction is basically a rearrangement of atoms. There are two types of chemical reactions. Number 1, exothermic reaction, and number 2, endothermic reaction. Exothermic reaction. In this reaction, the total energy of the reactants is more than the product of the reaction and heat is released. Endothermic reaction. In this reaction, the total energy of the reactants is less than the products of the reaction and heat is absorbed. Electrical energy. Electric charges and currents attract or repel each other. Thus, work needs to be done in general to move them with respect to one another. The energy associated with this work is called electrical energy. Nuclear energy. Albert Einstein, 1879 to 1955, showed that mass and energy are equivalent and are related by the relation E is equal to mc square, where c is the speed of light in vacuum. There are two types of nuclear reactions. They are nuclear fusion and nuclear fission reactions. Nuclear fusion. The sun's source of energy is an example of nuclear fusion. In sun, 4 light hydrogen nuclei fuse to form a helium nucleus, whose mass is less than the sum of the masses of the reactants. This mass difference is called the mass defect. Delta M is the source of energy. Nuclear fission. Nuclear power plant uses controlled nuclear fission. In fission, a heavy nucleus like uranium-235-92 is split by a neutron into lighter nuclei. The final mass is less than the initial mass and the mass difference translates into energy. Conservation of energy. Principle of conservation of energy states that energy may be transformed from one form to another, but the total energy of an isolated system remains constant. Energy can neither be created nor be destroyed. The universe can be viewed as an isolated system. The total energy of the universe is constant. If one part of the universe loses energy, another part must gain an equal amount of energy. Power. Power of a body is defined as the rate of doing work by the body. Let us take an example. A boy doing exercise by using dumbbell. When he used the dumbbell of 5 kg, then he applied power P1. And when he used the dumbbell of 10 kg, then he applied power P2. Hence, the power rating is high when he used the dumbbell of 10 kg as compared to the dumbbell of 5 kg. Power is a scalar quantity and is represented by P. Power of a body is given by P is equal to W upon T. Its SI unit is watt. Other commonly used units of power are kilowatt and horsepower. 1 horsepower is equal to 746 watts. Instantaneous power. It is defined as the average power in a very short interval of time at a particular instant. Collisions. Collision between two bodies is defined as the process of mutual interaction of the bodies for a very short interval of time, due to which energy and momentum of the interacting bodies get changed. Collisions are of two types. Number 1. Elastic collision. It is a type of collision in which both the momentum and kinetic energy of the system remains conserved. Number 2. Inelastic collision. It is a type of collision in which momentum of the system remains conserved, whereas kinetic energy of the system doesn't remain conserved. Elastic collision in one dimension. It is an elastic collision of two bodies, such that they move along the same straight line before and after the collision. Elastic collision in two dimension. It is a type of elastic collision in which bodies do not move along the same line after the collision, but they move in the plane containing the line of their motion before collision. Did you know? James Watt was born in a business family. He practiced engineering in Scotland. He improved the steam engine to such an extent that most people now think Watt to be an inventor of steam engine. It is interesting to note that the steam engine was originally developed by Newcomen. Work is energy transferred to or from an object by means of force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. The concept of potential energy exists only in the case of conservative forces. 1 erg of work is said to be done when a force of 1 dyne displaces a body through 1 centimeter in its own direction. Summary. Let us summarize what we have learned. Work is said to be done by the applied forces when the body on which the force acts suffers a displacement in any direction except perpendicular to the direction of force. When the work done is positive, there is an increase in the kinetic energy of the body. Area between the Fs graph and the S-axis gives the work done. Power of an agent is the ratio of the total work done by the agent to the time taken by it. It is a scalar quantity. Energy of a body is the capacity or ability of a body to do work. Mechanical energy is of two types, kinetic energy and potential energy. According to work energy theorem, the work done by a force is equal to the net increase in the kinetic energy of the body. According to the law of conservation of energy, the sum total of energy remains constant. When two bodies physically collide against each other, or when the path of one body is changed just by the influence of the other body, then collision is said to take place.